Okay, it's my pleasure to introduce Jade Brisson, speaking on upper bounds and spectral ratios and gaps for Steklov eigenvalues of work products. Thank you.
Thank you. First of all, I want to thank the organizers for the opportunity to speak today. What I will be talking about is multiple works that have been made with Bruno Colbois, Kitty Gittins, and also, if I have the time, I will talk about a project that it's ongoing with Bruno, Kitty, and also Alexandre Giroir. So. Okay. So what I'm doing, I'm working in spectral geometry. So first of all, I want to make a little overview of what spectral geometry is. So what we want to do is to find links between the geometry of a manifold and the eigenvalues of a problem defined on it. So the classical problem that we can think of is the Laplace problem. And if the manifold has a boundary, we can either put the Dirichlet boundary condition or the Neumann boundary condition. And we can find those links from various point of view. So we can find, for example, lower and upper bounds that involve geometric quantities, such as the area of the manifold, if we're in 2-dimension, the volume of the boundary, its number of boundary components, the genus, etc. And we can find those lower bounds for the eigenvalues, but we can also find lower upper bounds for the ratio of the eigenvalues and also the spectral gap. And we can also talk about optimization problems. So we can think about maximizing or minimizing the first eigenvalue among domains that respect certain geometric properties, such as convexity, with fixed area, with fixed perimeters, things like that. The problem that I'm interested in is the Steklov problem. So we need to define the Steklov problem on a manifold with a boundary. And we define it that way. So we call a real number sigma a Steklov eigenvalue if there exists a non-zero function f such that f and sigma satisfy the following problem. So first, we want our function f to be harmonic on our manifold M. And on the boundary of our manifold, we want the normal derivative of f to be equal to sigma times f. And we know that the eigenvalues form an increasing sequence of real positive number. So in the first sequence here, the eigenvalues are repeated according to multiplicity. And in the second sequence here, we have our index in parentheses. So this means that we consider the distinct eigenvalues. So here on the second sequence, we don't consider the multiplicity. And this notation is really important because I'm going to be using it throughout the presentation, either for the Steklov eigenvalues and also for another problem that we will be seeing a little bit later, but I will be using the same notation. So every time we see the index in parentheses, this means that I'm considering the distinct eigenvalues. And I'm going to be considering the Steklov problem on a specific type of manifold. So what we were interested in was warped product. So what is a warped product? So we consider a simple product, omega times sigma. So omega is a manifold with a boundary, and sigma is a closed manifold. So it's a manifold that it's compact and doesn't have a boundary. And we equip this product with the following metric. So we consider the metric G omega, so the metric on omega, and G sigma, the metric on sigma. And the metric on the product is G sigma plus H squared times G sigma, where H is a smooth positive function defined on omega. And also, we will be considering, it can be seen as a specific type of warped product. So it's balls with a revolution type metric on it. So what I mean is that we consider the product, the interval 0r times the sphere of dimension n minus 1. And we consider the same type of metric. So the metric dr squared, so the metric on the interval, plus h squared times the round metric on the sphere. But here h is not only a smooth positive function defined on an interval, but we need to specify other hypotheses. So we will specify that h in big R is equal to 0, which means that we have one boundary component. So the center of the ball is when R is equal to 0, and the boundary of our ball corresponds to small r equal to 0. And also we will add hypothesis on the derivatives of h, just to make sure that the metric that we're considering is smooth enough. And what we were interested in is, first of all, we wanted to consider the spectral ratios and spectral gaps of the Steklov eigenvalue on our balls with revolution type metric. And what we wanted to do was to find if they are bounded or not. So spectral ratios and spectral gaps have been considered for other problems. So first of all, Payne, Polya, Van Berger conjectured that the first Dirichlet spectral ratio, so the ratio of lambda 2 over lambda 1, was minimal for the disk in R2. Later on, Thomson made the same conjecture, but in higher dimension, so that the first Dirichlet spectral ratio was minimal for the ball in Rn for n greater than 3. And both conjectures were proved to be true. This was proven a few years later. For the Neumann spectral ratio and the Steklov spectral ratio, it was proven that it can be made arbitrarily large. So for the Neumann spectral ratio, to prove that it can be made arbitrarily large, we consider Chigger dumbbells. So we have, let's say we want to prove that lambda k plus 1 over lambda k is large. So we consider k domains that we join by a small interval, such that it looks like kind of k dumbbells put together. And for the spectral ratio, we consider k overlapping domains. So for example, k overlapping disks, and when we take the limit as the overlapping is made smaller and smaller, so that at the limit we obtain disjoint domain. So with that, we can prove that the ratios are arbitrarily large. And also, for the spectral gaps, they have also been studied. So it was proven that the first Dirichlet and Neumann spectral gaps, so lambda 2 minus lambda 1, are both minimal for the line segment among all convex domains in Rn. So for any n greater than 2. And also we have some results for the Robin eigenvalues for the spectral ratio and spectral gaps of rectangles under various geometric constraints. So this was made by Logesen. Going back to our balls with revolution type metrics, they have been studied previously by Xiong, but he added 2 more assumptions. So first of all, he added that the boundary to be strictly convex, and also he added assumption for the Ricci curvature. So he considered either non-negative Ricci curvature or non-positive Ricci curvature. And what he obtained upper bound and lower bounds for the spectral ratio and the spectral gap. So first, he proved that if the Ricci curvature is non-negative, then the spectral ratio of sigma k plus 1 over sigma k is smaller or equal than k plus 1 over k. And for the spectral gap, he proved that sigma k plus 1 minus sigma k is greater than h prime in 0 over h evaluated in 0. And also proved that we have equality in both cases if and only if our ball is isometric to the Euclidean ball. And for the non-positive Ricci curvature case, he proved the same inequalities, but they are reversed. So for the spectral ratio, it's a lower bound, and the spectral gap, it's an upper bound. So from those results, what we asked was, are the assumption on the Ricci curvature and on the boundary really necessary? So if we remove those assumptions, can we still have upper or lower bound for the spectral ratio and spectral gaps? So for the spectral ratio, we do have, in fact, an upper bound. So what we prove is the following. So if lambda k, in parentheses, so the k distinct Laplace eigenvalue of the n-1 dimensional sphere, we prove that for each function h satisfying a revolution type metric, we have that the spectral ratio of sigma k plus 1 over sigma k is always bounded above by lambda k plus 1 over lambda k. And this inequality is strict. So this means that there is no function h for which we have equality. However, the upper bound is optimal in the sense that the supremum over all h that satisfy a revolution type metric of our spectral ratio is equal to lambda k plus 1 over lambda k. So what I will be doing, so in this presentation, we'll be seeing a lot of ideas of proof because they are quite nice and quite simple. So the idea will always be the same. So we try to solve the Steklov problem. And since we are on a product, we can try to use the separation of variables to solve the Steklov problem. So what I mean is that we are guessing that the Steklov eigenfunctions are the following form. Are the form of a function AL defined on the interval 0R times a certain function on the sphere. And we replace this in our Steklov problem. And what we obtain is that the functions on the sphere are the solution of the Laplace problem for the sphere. And the function in the intervals satisfy the following problem. So AL satisfy an equation of degree 2 with the following condition. So we want the function A evaluated in R to be equal to 0. And we have the following condition for the boundary with our Steklov eigenvalue. And also with this problem for the function A, we obtain the following variational characterization for the Steklov eigenvalue. So this variational characterization is really useful because it can help us to find upper bound for the Steklov eigenvalue. And what we will be doing is to use a useful test function in the variational characterization for sigma k plus 1. So in order to obtain our upper bound for the Steklov ratio, we will try to find an upper bound for sigma k plus 1 with a useful function A. So the useful function that we will choose is the eigenfunction for sigma k. So the function that satisfies the problem here when L is replaced by k. And we use it in our variational characterization. So you obtain the sigma k plus 1 is bounded above by the following integral. And what we want to do at this point is to make sigma k appear somehow. And it's quite easy because we have its eigenfunction. But what's missing in the integral in order to have sigma k is this term. So the term lambda k times ak squared times h minus times h exponent n minus 3. So we add this missing term, but in order to have equality between the first integral and the second line, we need to remove the same term that we added, and also we will multiply and divide by lambda k. So we have equality between the first integral and the second line. So now the two first terms of the integral are equal to sigma k, and this on the third term, so lambda k a squared h n minus 3 is only one part of the variational characterization for sigma k. So this term must be smaller than sigma k. And at this point, what we need to do is only make a little bit of algebra to obtain at the left-hand side of our inequality sigma k plus 1 over sigma k. And what we obtain on the right-hand side will be lambda k plus 1 over lambda k. So this proves our upper bound. To prove the optimality, we need to choose a sequence of function h such that when epsilon tends to 0, our spectral ratio will tend to our upper bound. And the sequence of functions that we choose, we have two choices. So the first one is that we choose h epsilon to be very large on a substantial part of the interval. So let's say between epsilon and r minus epsilon, we want h to be equal to 1 over epsilon, so really, really large. Or we can choose h epsilon to be really small between epsilon and r minus epsilon. And on the missing intervals, we make sure that everything is smooth so that we satisfy our assumptions on the derivative. So I'm going to skip this theorem and maybe go back to it if I have time. So this is what we proved for the spectral ratio. But we were also wondering what happens to the spectral gap if we remove the assumption on the Ricci curvature and on the boundary. So what we observe is that with our construction, our previous construction to prove the optimality, so with our sequence of h epsilon, we prove that if h is really large, then the spectral gap is arbitrarily large. And if we chose h to be very small, then the spectral gap can be arbitrarily small. So in order to have an upper bound for the spectral gap, we might need an extra assumption on the function h. And this extra assumption is that h is bounded above by a certain constant on the interval. This is the only assumption that we need. And if h is bounded above by a constant, then the spectral gap is bounded above by the following upper bound. That involves the constant c. But I forgot to say that this is only when the dimension is greater than 4. So if the ball is of dimension 3, with our construction with either h large and h small, we do not have that the spectral gap is arbitrarily large. which means that the spectral gap is always bounded above, even if H is not bounded by a constant. In fact, we have the following. So the spectral gap is bounded above by the following upper bound. And moreover, the upper bound is also optimal in this case, with the same meaning as before. So the supremum among each function h of the spectral gap is equal to our upper bound. So we do not have the existence of a function h for which the spectral gap is equal to the upper bound, but there is existence of a sequence of functions h epsilon such that the spectral gap tends to our upper bound.
Jade,
Yes.
I don't remember what is the dimension of the sphere. Is
So the spheres,
n-1 or
it's n-1, so that the product
so
of the interval and the sphere is n.
N, okay, thank you.
Yeah, so this theorem is for the sphere of dimension 2 times the interval, and for the previous is the sphere dimension n greater than 3.
Okay, thank you.
So again, let me show you the ideas behind the proof of both theorem. So we will see why in dimension greater than 4 we need an extra assumption for h, because the first steps of both of the proof of both theorem are the same, but at some point we will need two different directions. So first of all, we start with the inequality that we obtain for the proof of the spectral ratio, so the upper bound for the spectral ratio. But instead of using the algebra to obtain sigma k plus 1 over sigma k, we will use different things to obtain sigma k plus 1 minus sigma k. So we subtract sigma k from both sides of the inequality. So on the right-hand side, we only have this term. So lambda k plus 1 minus lambda k times sigma k over lambda k. But on the right-hand side, we don't want sigma k anymore. So we don't want the Steklov eigenvalues. So what we need to do is to find an upper bound for sigma k. And again, we will use our variational characterization with a useful test function. But we won't be using the eigenfunctions of the Steklov eigenvalues because, well, we already used it to obtain the inequality. So we need another useful test function, and the test function that we will be using is the following. So we want a to be equal to 1 over a large part on the interval 0r, and then we need to kill it because we want a to be equal to 0 in big R. So we use a simple function. Now, I will just show everything. Okay. So if I use my test function in the variational characterization, what I will be obtaining is that sigma k is bounded above by the following integral. So in order to obtain an upper bound, I need to bound h somehow. And what we can do is use the assumption on h that we already know. So we already know that in big R, h is equal to 0, and that its first derivative in big R is equal to -1. From those two, we can say that there exists a row positive such that for each small r between r minus rho and r, so a small interval, then h is bounded by the following functions. So at the end of our big interval, if epsilon is small enough here, then we can say that H is bounded. But on the other part of the interval, we don't know if H is bounded or not. And this is a problem if the dimension n is greater than 3. Because if n is equal to 3, then h to the power of 3 minus 3, we don't have h anymore. So we don't need an upper bound for h between 0 and r. We only need it for the small part at the end of our interval. So what we already know. However, if the dimension is greater than 4, then h is present here, and we need to know if h is bounded between 0 and r minus epsilon. So this is why we need to add the assumption that h is bounded above by a constant. So if we do the calculation, we obtain the following upper bound in dimension 3. And in dimension 4, adding the assumption that h is bounded by a constant, we obtain the following upper bound. And then we use those upper bounds in the first inequality that we obtain. No, not this. I will go back. So we use the upper bound in the inequality right here. So we obtain the upper bound for the spectral gap. So at this point, this concludes the proof for dimension greater than 4. In dimension 3, I said that the upper bound for the spectral gap was optimal. So we need to show that it is optimal. To show optimality, first we need to fix the value of h in 0. Otherwise, it will be quite tricky to show the optimality. So we fix this, and then we assume that the upper bound for sigma k is optimal. And this is what I will be talking about in a few moments. But first, we assume that the upper bound is optimal. So this means that there exists a sequence of h epsilon such that my upper bound for sigma k, when epsilon tends to 0, then sigma k tends to its upper bound. So for each index L, so for each L greater than 1, sigma L tends to its upper bound. So here sigma k tends to r lambda k over h square, and sigma k plus 1 tends to r lambda k plus 1 over its square, and etc. for each index. What we do is that we rewrite sigma k plus 1 in the following way. So we can say that sigma k plus 1 is equal to sigma k plus 1 minus sigma k plus sigma k. And then we go on. So we subtract each eigenvalue that is of index smaller than k and add it again so that we still have equality. So sigma k is equal to the following sum, the sum of the following spectral gaps. We have proved that the spectral gaps are bounded above by the following. So each term here is bounded above by the following upper bound. So there's a mistake. So here there is no B2. And if we rewrite this sum now, we will see that there's a lot of terms that are canceling out each other. And the only term that's left is r lambda k plus 1 over h squared, which is the upper bound for sigma k plus 1. But when epsilon tends to 0, we know that sigma k plus 1 tends to its upper bound. So we have the same thing on each side of the inequality when epsilon tends to 0, which means that each spectral gap must tend to its upper bound. So this proved the optimality. The only thing that's left is to prove that the upper bound that we have found for sigma k is optimal. And this is the second part of my talk. So this is the other question that we were interested in. So first of all, we were interested in studying the spectral ratios and spectral gaps of balls with revolution type metrics. But we were also interested in following upper bounds for the eigenvalues of warped product and also for balls with revolution type metric. So why we wanted to find upper bound for warped product? This is because of the following remarks made by Caubois et Sophie and Giroir in one of their articles. So they proved that for a warped product with the fiber, so the warped product is omega times sigma. So if sigma is of dimension greater than 3, then they proved that the first Steklov eigenvalue can be made arbitrarily large. However, they pointed out that if sigma is of dimension 2, then the first Steklov eigenvalue is always bounded above by r times lambda 1 over 2. So here, lambda 1 is the first Laplace eigenvalue of sigma, and r is the length of our interval. So from this remark, what we can ask is this upper bound optimal? So can we find a function h for which sigma 1 is equal to the upper bound? Or can we find a sequence of functions such that sigma 1 tends to the upper bound? And also, can we find upper bound for each eigenvalues? So we're not only interested in the first eigenvalue, we want to find upper bound for each eigenvalues. And this is what we did. So we proved that if we consider the following product, so 0r times sigma, so really a general warped product with sigma of dimension 2, we equipped this product with the warped metric. So h is a smooth function on the interval 0r. And just to simplify the calculation, we fix the value of h on the boundary of the interval, and we fix it to be equal to 1 in both end of the interval. So here in this case, what's different than with balls with revolution type metric? So here in generality, we have 2 boundary components. And for the balls with revolution type metric, you only have 1 boundary component. And the proof here, so the theorem 5 works also for this special case. So the upper bound that we found here, this is of the same type than that for balls with revolution type metric. So we prove that sigma k is bounded above by r times lambda k over 2. And that this upper bound is optimal in the sense that there exists a sequence of function such that sigma k tends to the upper bound. So last proof, the ideas, as I said, are always the same as before. We're on a product. We can try to solve the Steklov problem by using the method of separation of variable. So we suppose that the eigenfunctions are the form a function on the interval 0r, times a function on sigma. And we obtained that the function on sigma must be an eigenfunction for the Laplace problem. And here A satisfies the following problem. So what's different here? So we have 2 boundary components, and we don't have the assumption that A must be equal to 0 in big R. So this is the 2 difference with the ball with balls with revolution type metric. So if we don't have the assumption on A in big R equal to 0, we have that for each L fixed, we have two eigenfunctions. So since it's an equation of degree 2, we have two possible functions that satisfy the equation. However, for balls with revolution type metric, since we want the eigenfunction to be equal to 0 at one point, this eliminates one function. But here it's not the case. So both functions are admissible. And for each function, there is an eigenvalue associated to it. So those eigenvalues will be denoted sigma L0 and sigma L1. And for each of those eigenvalues, we also have a variational characterization. So here we have proven that the Steklov eigenvalues are given by sigma L0, sigma L1 for each L greater than 0. So for each index L. But if we want to order them, so we want to say the first one is equal to sigma L0 for L equal to I don't know what index, this is hard. So in general, we cannot order them. But what we can say is that the kth Steklov eigenvalue is always smaller than sigma k0. So if we want to find an upper bound for sigma k, because that's what we wanted to do, we only need to find an upper bound for sigma k0. So this is much easier since we cannot order them. And to find an upper bound, we use the variational characterization with a good test function. So the variational characterization that we use is the first one for sigma L0. So here, the minimum is among any function A that is not 0. So the easiest one that we can choose is the constant function. So if we choose the constant function, let me go back, it's not written. If we choose the constant function, here the derivative will be equal to 0. So this term is equal to 0. And what's left is the integral between 0 and r of lambda L times r constant squared. So we can choose the constant 1 since it's simple. So on the numerator, we obtain lambda L times r. And on the denominator, we obtain 1 plus 1, so 2. So we obtain our upper bound. To prove the optimality, again, we need to choose a good sequence of function h, but here it's a little bit trickier than before, since we cannot order the eigenvalues. So for the sequence that we choose, we need to make sure that the first, let's say k plus 1 eigenvalues, so we fix the number of eigenvalues that we want to be equal to sigma k0. So we cannot say that the ordered eigenvalues are sigma 0, 0, sigma 1, 0, sigma 2, 0, etc. But what we can do is fix an integer, so let's say big K, and we can say that the first k plus 1 eigenvalues will be of the form sigma k0. And after that, so the big K plus 2 eigenvalue, we don't know what it is, but it doesn't matter since for the first k plus 1, we can prove that the first k plus 1, our eigenvalue tends to our upper bound. And we can do this for each big integer k. And now, this is the part where I'll be talking about a little bit of the ongoing project. So what we have proven here, it's only when omega is of dimension 1. So word product of the form an interval times a closed manifold of dimension 2. However, for warped product, we're not obligated to consider an interval. We can consider any manifold with boundary, and we can ask the same questions. So we can ask, are the eigenvalues bounded above or not? Can they be made arbitrarily large? What can we say about the spectral ratios, the spectral gaps? And what we have proved so far is that the eigenvalues are bounded above. So we have proved that for any manifold omega with boundary and any sigma of dimension 2, and we equip this product with the Ward metric g omega plus h squared g sigma, where h is a smooth function on omega, and we fix its value on the boundary of omega just to simplify the calculation. Then we have proved that sigma k is bounded above by the following. So lambda k times the volume of omega over the volume of the boundary. So here again,
what is lambda k?
Yes.
That was my question. What is lambda k?
Yeah.
Sorry.
Lambda k again is the kth Laplace eigenvalue of sigma.
Thank you.
And again, we can prove that the upper bound is optimal in the same sense as before. So we cannot find a function h for which sigma k is equal to the upper bound. However, we can find a sequence of function for which sigma k tends to the upper bound. But here I'm not gonna show you the details of the proof because it's quite trickier than before. So if we consider dimension greater than 2 for omega, things get quite complicated because again, the idea is to try to use the separation of variable, but instead of obtaining here a quite simple differential equation for the function on omega, we obtain a partial differential equation. So this complicates things because we have an infinite number of function a that are admissible for the partial differential equation. So for each fixed L here, we don't have two eigenvalues, we have a sequence of eigenvalues. So this complicates things if we want to order the eigenvalues. And to show the optimality, also this complicates things. So what we did instead was to consider the L2 norms of the eigenfunctions and prove that the L2 norm tends to a constant. I'm not going to go into details, but the idea is using L2 norms. And I have a little bit of time to go back to the theorem that I skipped. So go back. So this one, okay. So here, let me recall that in this section, we were considering balls with revolution type metric. So the interval 0r times the sphere dimension n-1. And we were looking at the spectral ratio. And what we have proven before, so the first theorem was an upper bound for the spectral ratio. And we proved that the upper bound was optimal. And what we did here was to ask, is it, so to prove the optimality, we chose two sequences of function h epsilon. So either h was arbitrarily large or arbitrarily small. And here the question was, is this the only way to be close to the upper bound? So are there any other sequence of function, other type of function h, for which the spectral gap tends to the upper bound? And in fact, no, there are no other type of functions h epsilon to obtain, to tend to the upper bound. So if h is bounded above on a certain part of the interval and then bounded below, so we don't want h to be either really big or really small, so it's always between two constant, then we are far from our upper bound. And we are far from it by this certain constant gamma, which is explicit, but its expression is quite complicated, but it depends on C1 and C2, so our constant that we want to bound h between. It depends on R and on R1. So the R1 here, where we fixed h to be bigger and smaller than two constant. And it also depends on lambda k plus 1 and lambda k. And also what we can say is that if C2 tends to infinity, gamma tends to 0, and if R1 tends to 0, then also gamma tends to 0. So this means that to be close to our upper bound, we either need h to be really big or really small. So when C2 tends to infinity, this means that we need h to be really big. And if we tend R1 to 0, this means that we need h to be really small. And this concludes what I wanted to talk about today.
Thank you very much for a very nice talk. Are there questions?
I have a question, another question. Jade, I am curious about the condition at the very beginning,
Yes.
about the even derivatives vanish at R. This one, the last item there. What does it mean, or what?
So the first two assumptions needs to be there in order to obtain upper bound for the spectral gap. But the last one, I'm pretty sure we can relax them. We don't need them to obtain upper bound, but it's because Xiong, in his result, considered those three assumptions, plus the assumption on the Ricci curvature. But what we wanted to do was we didn't want to keep the assumption on the Ricci curvature, so we only kept those. And those makes sure that the metric is smooth enough. But I'm pretty sure that we can relax the last one. So we probably don't need them in order to obtain our upper bound, but we kept them just to be sure that everything was smooth for the metric.
Okay, thank you. And concerning the first theorem, when sigma is around the sphere. No, wait. Well, yes, this theorem. What about here? Sigma is the n minus one dimensional round sphere, right?
Yes.
And what do you expect if you replace this round sphere for another Riemannian manifold, or maybe another Riemannian metric on the sphere? Is it possible that?
Yeah, I think we will have the same result if we consider another metric on the sphere, since the upper bound doesn't depend on the metric. However, if we change the sphere for something else, so we try to obtain results in generality for a warped product of the same type, so an interval times a closed Riemannian manifold. But if we have two boundary conditions, it's really hard to obtain something for the spectral ratio because of the fact that we have two eigenvalues associated to each problem
What do
here.
you mean two? What do you mean two boundary conditions?
Not two boundary conditions. Sorry, two boundary components.
Okay.
Yeah. So here we have only one boundary component, so it's quite simple here. But if we have two boundary components, then we have two eigenvalues associated to each L, so we cannot order them. So it's quite difficult to say what is sigma k plus 1 over sigma k.
Okay, but you can assume that H vanish at some...
If we assume that H vanish, we will have the same upper bound. But here it will be the Laplace eigenvalue of sigma.
Yeah.
Oh, interesting. Interesting.
Well, that's nice. Huh.
Okay, that's all for me. Very nice talk. Thank you.
Are there any other questions? Okay, yeah, I had the same question, so thank you. Well, thank you very much for a very nice talk.
Thank you.
And I'll stop the recording. Let's see.